A pleasant day to you all. We are here to present our project study entitled Project Sagip, Speech and Gesture Recognition for the Control of Home Appliances, integrated with signal processing, machine learning, and deep learning.
With the fast approaching development and growth of technology in our era today, many individuals are having a hard time coping up in the trend and thus affecting their everyday living. These individuals are mostly the elderly people and people with disabilities. One good example of their struggle is their difficulty in controlling home appliances, and most of them require assistance from other people. In this project, the proponents created a system that is capable of controlling the most used appliances in a house by means of doing hand gestures or through speech recognition with the help of machine learning and deep learning. In this way, the elderly people and people with disabilities can control different appliances based on their preference and to condition through the help of Kai gesture controller for gesture and a microphone for speech commands.
Objectives. In developing the entire project study, we established the general and specific objectives. Generally, our system classifies different commands in the form of gesture and speech to control basic home appliances in order to lessen the complexity and laborious tasks of the target users. In here, the mini computer of the central hub, which is supposedly the Raspberry Pi 3B Plus, was changed into upboard. This modification will be further discussed later on. So first, to attain the general objective of the project study, the specific objectives for speech includes to develop a system for speech recognition by utilizing a wireless microphone for controlling home appliances, which is integrated with signal processing, machine learning, and deep learning. Under this is to gather command audio files through a wireless microphone using the upboard. Next is to extract the mel frequency substral coefficients, or MFCC, of each audio files. And last is to train three different learning models, namely Hidden Markov Model, or HMM, Dynamic Time Warping, or DTW, and Long Short-Term Memory, or LSTM, using the extracted MFCC with at least 90% accuracy. Second, the specific objectives for gesture is to develop a system for gesture recognition by utilizing the Kai gesture controller, which is integrated with machine learning. Under this is to gather gesture commands using the Kai gesture controller. Next is to extract the strings of each JavaScript object notation or JSON file, and last is to train three different machine learning models, namely Artificial Neural Network, or ANN, K-nearest neighbor, or KNN, and Support Vector Machine, or SVM, using the extracted strings with at least 90% accuracy. Third is to implement the most accurate learning model for speech and gesture recognition into the upboard. Fourth is to develop a central hub that will process the speech and gesture and will serve as a wireless interface for home appliances. Fifth is to create a graphical user interface, or GUI, to display the output. And sixth is to test the accuracy and reliability of this system.
The concept of the study is to provide a convenient and efficient way of operating home appliances with the use of hand gestures and speech recognition to become more user-friendly, especially for elderlies and persons with disabilities. For the input, the user has the privilege to use their hand by doing hand gestures by using Kai gesture controller, or by speech by simply saying different commands to operate the desired home appliances using wireless microphone. The Kai gesture controller is linked to the upboard via wireless connectivity using its USB dongle, while the receiver of the wireless microphone is directly connected to the upboard via its USB port. The upboard will serve as a mini computer that processes the input and give commands to the home appliances in line with the classified hand gesture and speech command that is performed by the user. Since upboard has no built-in Wi-Fi module, the proponents connected Wi-Fi module to the upboard so it will be able to communicate with the home appliances. The proponents uses a Wi-Fi router to have a wireless, seamless, and efficient way of connection of the central hub and the appliances. For the output of the system, a 7 inches TFT touchscreen display will be used for the system to make it more interactive to the user. The appliances to be controlled are also part of the output, specifically the television, electric fan, aircon, MP3 player, and light bulbs.
For the block diagram of the system is subdivided into three parts, mainly the input part, the process part, and the output part. The Kai gesture controller and the wireless microphone will serve as the input medium for the system, and Kai is responsible for the acquisition of gesture commands, while the wireless microphone is for the acquisition of speech commands. The gathered input data will go onto the central hub for the process of deep learning and machine learning. The central hub consists the upboard that will process the input from Kai, and the microphone and the output will be displayed on a TFT screen to make it more user-friendly. Lastly, in order to execute commands from the appliances itself, a Wi-Fi module is connected to the upboard, and every appliance will have an Arduino Uno with Wi-Fi module to relay its information back and forth to the central hub, a logic level converter that will match the voltage output of the devices in order to avoid damage in the long run, an IR transmitter for the acquisition of infrared signals from the remote of appliances to be copied in the system, and a servo motor, but only for the lights to have a variation of its desired brightness.
Hardware. The different components that was incorporated in the system will be discussed in their specific functions needed in the system. The following are the hardware components used in the project Sagip. First, upboard. Upboard is located on the central hub. It serves as the brain of the system. It is the microprocessor that will process the input from the Kai gesture controller and wireless microphone. Second is a 7 inches touch screen display. It is attached in the front of the central hub. This will display the interface of the menu for speech and gestures. The system becomes more interactive because of the display. Third is the Arduino Uno. This component will be the bridge in the wireless connection of the central hub, specifically the upboard and the appliances. Fourth is the Wi-Fi module. This component will be attached in the Arduino and upboard for communication purposes. Next, the logic level converter. This device is used for automatically switching the voltage depending on the voltage rating of other devices. Next is the IR transmitter. It is attached in each Arduino and should be placed in front of the IR receiver of each appliances. Kai gesture controller. It is used by the user to make gestures for operating home appliances. Lastly, wireless microphone. Wireless microphone will be used so the user can use it much easier without going near the central hub because of its wireless connectivity. This will be used by the user to operate home appliances through speech commands. The construction of the Project Sagip casing was designed with respect to various parameters. The proponents came up with such a portability, stability, and aesthetics. Acrylic board material was used because of its incredible durability and portability. The proponents were able to design a central hub which contains the equipment necessary for controlling home appliances. The equipment inside are the TFT display, Wi-Fi module, and upboard. The casing for the central hub and Arduino were already built but without aesthetics. Furthermore, the materials needed inside the central hub are not gathered in one place because of the unexpected cancellation of classes and followed by the enhanced community quarantine due to the COVID-19 pandemic. Thus, the development and also the assembly of central hub were not yet finished. Software. Through extensive research, the proponents successfully built different learning models for gesture and speech classification. Through the programming language, such as Spider, the codes were properly settled and embedded in the microprocessor, which is the upboard. The proponents developed necessary codes for data gathering, training of 5 machine learning models such as ANN, KNN, SVM, HMM, and DTW, and 1 deep learning model, which is the LSTM, and the graphical user interface. The proponents were able to connect the developed model to the GUI. The algorithm and flowchart of these models are furtherly discussed in the Chapter 4, while the codes of the models can be found in the Appendix G of the manuscript.
Data analysis and interpretation of result. The proponent developed gesture recognition and software recognition acquisition software through the use of Python. The gesture recognition acquisition software focuses on identifying the gesture commands from the output of the guide gesture controller, and it uses the finger shortcut data and the accelerometer of the guide to obtain the data. For the development of the speech recognition acquisition software, it focuses on classifying the speech command comes up from the input of the user from the wireless microphone. After acquiring 360 samples for gesture recognition for each class and 180 samples for speech command in each class, the acquired data were used to produce a dataset applicable for training. There are three learning models for classifying hand gesture, namely the artificial neural network support vector machine and the k-nearest neighbor port. And for the classifying of speech command, there are dynamic time wrapping, hidden Markov model, and the long short-term memory. And those Python script can be seen in the manuscript on Appendix C. And to acquire the most appropriate learning model to be used in the system, the proponents split the dataset into four partitions: the 90-10, 80-20, 70-30, and 60-40. And to acquire the appropriate model, the proponent acquired the training results and confusion matrix of each learning model with a different partition.
Based on the results of the gesture classification models that was developed by the proponents, it can be seen that ANN, SVM, and KNN got its highest accuracy with a data splitting of 80-20. ANN got 94.11%, SVM got 93.97%, and KNN got 94.59%. Among the three classification models for gestures, KNN got the highest accuracy. While for speech, based on the results of the speech classification models that was developed by the proponents, it can also be seen that DTW got its highest accuracy in 90-10 data split ratio setup with 80.36 accuracy. HMM got its highest accuracy in 90-10 data split ratio set up with only 3.92% accuracy, while LSTM got its highest accuracy with a data splitting of 80-20 with 92.56% accuracy. Among these three classification models, for speech commands, LSTM got the highest accuracy.
The proponent created a classifier report for each learning model, which include precision, recall, and F1 score for better visualization. For a detailed result, it can be seen in our manuscript. And after analyzing the different classification model for each learning model, the proponents concur the most appropriate machine learning for classification of the gesture is the k-nearest neighbor, having an accuracy of 94.59%, and for classifying speech command is the long short-term memory, having an accuracy of 92.56%, and both learning models use the split partition of 80-20.
After knowing the best model for gesture recognition, using the evaluator script, the gesture commands were repeated 6 times, 3 times for the right and another 3 times for the left. This is because Kai gesture controller can be worn with either hands depending on the comfortability of the user. To test the whole accuracy using gesture recognition, the proponents have 25 random gestures to test the accuracy of the system. 24 out of 25 tests are successful and the only failed gesture is the fan off. The output of the gesture fan off is the command swing off. The reason behind it is because the gesture of both swing off and fan off are slightly similar. The gesture swing off is all the fingers are closed, while in the fan off, only the pinky finger is open. Therefore, the result of the accuracy of the gesture recognition subsystem is 96%.
After knowing the best model for speech recognition, the proponent evaluate the generate model for using the evaluator script, and each speech command repeated 3 times to ensure the accuracy per commands for appliances. And based on the result, almost all the appliances got 100% of accuracy except for the pan, since the system failed in the speech command of increased speed and decreased speed and getting the accuracy of 88.89%. Since the increased speed and decreased speed are almost alike, And for the detailed result, it can be seen in our manuscript. And to get the accuracy of speech recognition, the proponent have a 25 random test to eliminate the bias on the training and get a result of 100%. And to get the whole accuracy of the project Sagip, the proponent used the formula of whole accuracy of the system is equivalent to the accuracy of gesture plus accuracy of speech all over 2 multiplied by 100 and get a 98% of accuracy. In order to assess the reliability of speech recognition of the system, the proponent tests it into three different noise levels. It starts from 50 dB, 60 dB, 70 dB to determine if it's still reliable to use. And in each noise level, the speech command repeated 3 times. And the proponents garnered in 50 dB level 97.62%, and in 60 dB level it's 92.86%, and lastly for the 70 dB level it's 90.48%. And based on the result, it concluded that as the noise increases in the surrounding, the system increases the failed remarks and decreases the reliability of the system. And the most error terms in reliability is the speech command of increase speed and decrease speed, fan on and fan off, aircon on and off, and the swing on and off. And to get the total reliability of the system, the proponent have a 25 random test into 3 different noise levels to prevent any bias in the training and get a 88% of reliability. The system may not recognize clearly the commands because of the increasing noise of the surroundings, but in total, the project Sagip is functional and reliable to use in a house for daily usage.
Conclusion. First, for speech, we are able to develop a speech recognition system to control home appliances using a wireless microphone. Under this, we are able to obtain command audio files from different respondents through the use of a wireless microphone, and using the same device, speech commands were recorded and transferred into the output. Next, all data were run through an MFCC extraction program, and the extracted FFCC of each audio files were stored as CSV files and serve as input to the speech recognition training. Lastly, training of 2 machine learning models called HMM and DTW and 1 deep learning model called LSTM were done. After the training, LSTM exhibits the highest accuracy of 92.56% compared to 3.67% of HMM and 74.21% of DTW, with 80-20 splitting ratio for training and validation. Second, for gesture, we are able to develop a gesture recognition system to control home appliances using the Kai gesture controller. Under this, we are able to obtain gesture commands from numerous respondents through the use of the Kai gesture controller. And using the same device, gesture commands were recorded and transferred into the output. Next, JSON format is an output of the Kai gesture controller, which cannot be directly fed into the machine learning. Thus, we develop a parser to extract the generated JSON strings and access the numerical values of the gesture performed. The extracted numerical values of each gesture command serve as input to the gesture recognition training. Thus, the training of 3 machine learning models, namely ANN, KNN, and SVM, were done. Among all learning models, KNN shows the highest accuracy of 94.59% comparison to 94.11% of ANN and 93.97% of SBM, with 80-20 splitting ratio for training and validation. Third, we are able to implement and embed the cell classifiers in the upboard, but the MIDI computer is not used for testing the system due to the same reason which will be stated later on. From the aforementioned statements, LSTM and KNN yielded the highest accuracies. Hence, LSTM and KNN are the final machine learning classifiers utilized in this study. Fourth, we are able to design and build the casing for the central hub. However, objective number 4 was not fully met due to sudden and unexpected cancellation of classes followed by the enhanced community quarantine caused by the COVID-19 pandemic. Moreover, the components and materials for the central hub are not gathered in one place because of the same reason. Thus, the development and assembly of the central hub were not finished. Fifth, a graphical user interface is developed to display and to test the user's specific gesture or speech command. This is to visualize and check whether the classified speech or gesture command is correct. 6. Objective number 6 was not fully achieved since we are unable to test the accuracy and reliability of the system by controlling home appliances using the design central hub. However, we are able to test and evaluate the system's accuracy and reliability through the use of the evaluator script connected to the GUI. Testing and evaluation are done by utilizing the developed GUI, which displays the classified gesture or speech command performed by the user. From this, the accuracy of the system obtained was found to be 98%, while its reliability was determined to be 88%.
Recommendation. Here are some suggested recommendations of the proponents for the future researcher for further improvement of the project Sagip. The future researcher should use a fully developed KAI gesture controller with the latest version of it to maximize the use of the features of the said device. Also, to explore thoroughly the device to be used in the system to know the capabilities and limitation of the device. To add 2 or more KAI gesture controller and a wireless microphone in the system to be used by a multiple user. Also include more speech and gesture command and brands of appliances to be more reliable. And lastly, the future researcher should put a security feature for the device, the system, for the protection of the information of the user.
For gesture and speech evaluation, each class will be tested in their corresponding commands. The gesture commands will be tested by using KAI gesture controller, and for the speech command, it will be tested using wireless microphone.
For the visual presentation, the graphical user interface will be presented in laptop because the components, specifically KAI, upboard, microphone, and the 7-inch display, were held separately by the other components. The GUI is composed of a homepage for the presentation of commands, choosing appliances brand page for a specific type of brand in TV and aircon, help page for instructions of GUI, and about page for the project's description. First of all, before testing the commands, the KAI controller and wireless microphone must be properly set up. For the KAI gesture controller, connect the USB dongle of KAI to laptop. And then, install the control center of KAI, which can be downloaded through their website. After installing, calibrate the KAI gesture controller while following the steps presented in Control Center. Calibration complete. Continue. Then click right hand for the calibration and then start. Calibration complete. Continue. Follow the gestures.
and your coin was successfully recalibrated. And now, for the wireless microphone, first of all, turn on the power-up microphone headset and the 3.5mm jack receiver. In pairing the two devices, long press the headset match code. Then after blinking 3 times, click the receiver match code. And then, click the headset match code for confirmation. After pairing, connect the 3.5mm jack receiver to the laptop and the wireless microphone is ready to use. After setup, we will test now all of the gesture and speech commands using these devices. We will start first in gestures. Aircon on. Aircon off. Channel up. Channel down. Fan on. Fan off. L1 on. L1 off. L2 on. L2 off. MP3 on. MP3 off. Next, previews. Speed up. Speed down. Swing on. Swing off. Temperature up. Temperature down. TV on. TV off. Volume up MP3. Volume down MP3. Volume up TV. Volume down TV. And now, we will try the speech commands. In order to speak the commands, we must use the activate speech using the gesture controller. Once you activate it, you are ready to speak the different classes. Aircon off. Aircon on. Channel up. Decrease speed. Fan off. Fan on. Increase speed. L1 mid. L1 off. L1 on. L2 mid. L2 off. L2 on. MP3 down. MP3 off. MP3 on. MP3 up. X. Previews. Swing off. Swing on. Temperature down. Temperature up. TV down. TV off. TV on. TV up. Channel down.
For the reliability of the speech recognition, we use the 50 decibels, 60 decibels, 70 decibels noise level environment. But due to the recent pandemic, some components were held by different proponents and we were not able to use the sound level meter for identifying the noise level. In that case, the group researched about the comparative examples of noise levels to achieve the decibel level for evaluation. The 50 decibel is compared to a quiet conversation or minimum sound which is 1/4 as loud as 70 decibels. Next is 60 decibels compared to background music which is half as loud as 70 decibels. Last is for 70 decibels compared to living room music, a TV audio sound, or a very loud music.
L1B. Channel up. Aircon on. Aircon off. Fan off. L1 on. L1B. L2B. Fan off.